yesterday, so I'm going to concentrate on low energy quenching of GA. So I excuse a bit because I mean this is a very vast topic. I have to skip some things like accelerator studies of quenching in neutrino nucleus scattering. I have to skip something about giant states of isovector spin multipole resonances. I also have to skip muon capture, which is also a possibility for GA quenching or pseudoscalar quenching and so on. So now I concentrate on low energy quenching here, which is relevant for double beta decays. So I mean double beta decay is an incentive here for this talk. And why is that? In 2 neutrino double beta decay, we go via these 1+ states here, and decay rate is quenched by this GA to the 4th power, which is very drastic quenching. I mean drastic relation, because if GA is quenched, as was mentioned yesterday, this might cause some difficulties for future experiments, especially for neutrinos double beta decay experiments, where you have the same problem here. I denote here this constant in a different way related to relative to 2 neutrino case, because I mean this is a higher momentum process here, so you can go via all multipolarities, as was mentioned yesterday, and these are not suppressed. These are forbidden, so to say, forbidden transitions, but they are not forbidden in this context because you have this large momentum transfer, so you actually excite this high lying state and higher multipolarities easily. So this is actually the actual incentive here. Try to get some hold of this quenching of GA, this effective GA, which I'm defining here. So this is the basic definition. You can get this quenching from experiments, for example, combined with theoretical analysis. And then you divide your GA, which you obtain from your analysis, with the free value, present free value of this coupling constant. And then you may give this quenching here to some other person. If this other person multiplies it by free value of GA, he gets the effective value of GA, possibly quenched value of GA. So these are the basic definitions. So now what do we learn? What have we learned along the years about the quenching or even enhancement of this GA? So first I touch the oldest possibility to study quenching, this Gamow-Teller beta transitions. And these studies have been mainly been performed in the form of interacting shell model for a long time already. Then there are some studies of RPA. In the RPA theory, I'm not going into details of these theories. I mean, it's impossible in this review. So I just tell about the results of different approaches. So these are now examples of Gamow-Teller transitions in different nuclei. You have this kind of cascade of decays here, which you can study. You can have lateral feeding of the central nucleus by Gamow-Teller transitions. Also, you can have a double beta decay-like situation where the intermediate nucleus is feeding by Gamow-Teller transitions the initial and final states of double beta decay. So let's take a look at interacting shell model calculations and the quenching which is obtained in those calculations. This is a list, almost complete list of different calculations along the years, starting from the 70s. There was a great interest during those days to this kind of quenching phenomena, and these quenchings were studied in the P shell, SD shell, PF shell, BFG shell and extended BFG shell and so on. Along the years, of course, I mean, computing power was growing and heavier nuclei could be attacked by these calculations. And most of these studies were done already quite some time ago. And only lately this problem with the GA was kind of re-emerging because of the needs in neutrino's double beta decay. So this is a kind of renaissance of GA quenching times. So, and let's see, this is of course, I mean, you cannot read all this, but I mean, this is a pictorial presentation of the same thing here. So along the years, of course, you can attack nuclei which are heavier and heavier. So these are different calculations now marked by the authors here. This is a list of these authors which are represented here. I mean, the results are represented here. And you see there is some kind of A dependence in these results. It means that the quenching seems to grow when the mass number grows. So this seems to be kind of general trend here based on these calculations. So next we can have a look at the RPA calculations and maybe compare these calculations with the shell model calculations to see what happens if there is any correspondence or correlation between these two models or predictions if two models, because they are totally different in a sense. But I'm not going into the details of structural theory. So here are some studies now, systematic studies, very recent ones, systematic studies of quenching of GA as a function of mass number. These are now representative of the error in the kind of determination of GA. I mean, it's a huge variation of GA from one nucleus to the other. That's why you have this, I mean, different patches there. These patches are actually hatched areas are divided according to the leading configuration in your matrix element. So this is kind of natural division line here. So you have these different mass numbers here represented by different leading proton-neutron configurations in the calculation. And then this division shows here as a slight mass dependence, kind of decreasing GA value, except here for the larger masses where there's a jump in the analysis. So now you can overlay this with the results from the shell model calculations. So the shell model calculations are here, and then these hatched areas of RPA calculations are background there, and as you can see, it is surprisingly consistent. I was surprised when doing this analysis. I was surprised to have so kind of similar trend in both types of calculations, in spite of the fact that the two theories are quite different. So this was somehow striking result, I would say. Then, of course, you can also study simultaneously single beta decays and double beta decays. And this was done by a few groups. These are examples here of 3 possible cases where you know both the 2 neutrino double beta decay half-life and then the lateral feeding with Gamow-Feldman transitions. So these are the only 3 cases which are there for our analysis. There has been a first analysis, kind of combined analysis was done by Armand and company a long time ago with least squares fit. This is kind of over-constrained problem here. You have 3 quantities which you can fit, and in RPA you have 2 free parameters. One is this GPP parameter and one is GA, effective quenching of GA. And you can perform this kind of least squares fitting fitting, or then a bit different type of analysis which we did, which gives more or less the same results. And now if you take a look at the results here and contrast these results against the single beta decay results of RPA, you can see that, I mean, there's again, I mean, striking similarity in the trend. These were presented by Franco already. I mean, this analysis which is giving this IBM model results and also interacting shell model, the parameterized curves here. But then in addition, you have this analysis coming from the Tübingen body collaboration and from Jyväskylä. And then there's also calculation in the interacting boson fermion model, which is of course, I mean, rather complex already, so I mean, not so easy to handle maybe. So, but I mean, all these trends point to the same direction. So the interacting shell model analysis, RPA analysis, and also this double beta decay analysis point to the same direction, which is rather striking, I would say. So now, of course, one can go beyond these allowed decays, and this is then you go to the realm of forbidden decays, and the most simple forbidden decays are the unique forbidden decays. It means that there is practically only nuclear matrix element which is mediating this transition. It means that it is like Kharmov-Teller-like in that sense. In fact, I was including the Kharmov-Teller to this list of transitions, kind of unified description of allowed and forbidden unique decays. So this is the basic structure here. It looks like very much like a Kharmov-Teller-like structure. So it is simple to analyze. Here you have the different multipolarities which you can access. The parity is minus to the k, parity change minus to the k, and the final state is k plus 1 if you start from 0 plus states as usually we do in our analysis. So these are quite simple in that sense. And the first of this kind of studies we did together with Jiri-san for dipole, spin dipole transitions. And you can see, I mean, we had analyzed something like 20 cases where there were experimental data on these nuclei, and we divided this to two parts, the analysis. This is the comparison of the experimental matrix element with the two quasi-particle approximation, which is a very simple approximation here, which takes somehow is the first approximation to these transitions. Then a more sophisticated theory, this RPA theory, was also compared with experiment, and the effective value, global effective value of GA was obtained from these transitions. So the first forbidden unique transitions between 0 plus states and 2 minus states. Again, you can also, I mean, somehow you have this kind of suppression factor which is coming from going more simple nuclear theory to more complex or complete nuclear theory. This is the kind of measure of the nuclear model dependence, because now it is not easy to separate the nuclear model dependence, as was mentioned, and the nuclear medium effect. The nuclear medium effect covers like delta excitation, non-nuclear degrees of freedom, but also two-body currents like meson exchange currents and so on, which were studied in the 70s quite much, but then somehow they were forgotten for a long time actually. So I mean, and now they are re-emerging again. So then we can also study unique higher forbidden decays. Again, this simple structure continues. I mean, you can analyze these transitions. This is one example here, 116 cadmium double beta decay. This is a neutrinos double beta decay feeding ground state of 116 tin. And the intermediate states consist of a collection of different multipolarities. 1 plus states are there This is the ground state actually, but then you have these red ones which are kind of reached by unique, highly forbidden, unique highly forbidden decays. And so part of these states are even isomers, so it means that the gamma decay half-life from those are quite high actually. So you have a nice collection of different possibilities, and in principle you could study maybe all these transitions, these virtual transitions by real transitions in some nuclei. And there are a lot of these nuclei. Unfortunately, there is no experimental data available. That's the problem. So, but we did a study of almost 150 nuclei of higher forbiddenness or transitions of higher forbiddenness. And here we were studying this quenching coming from the nuclear model. So, and what are typical examples here? This is one example, kind of cascade of decays, third forbidden decays. All these half-lives here are computed ones. I mean, they are not measured ones, but computed ones. I mean, with certain approximations or certain assumptions. Let's say this is prediction which where there are underlying assumptions, but I'm not going to details of that. Here also, I mean, you have a double beta decay-like situation, and again you have 4 forbidden transitions here with huge half-lives here. This is a double beta decay half-life. This is a single beta decay half-life. They are of the same order, so it might happen in several cases here actually. So these are typical examples, and this is now a scatter of different transitions in different nuclei of different forbiddenness. And you can see, I mean, at once you cannot see anything actually. So I mean, but I mean that is just to show that I mean there was some work done on this. And if you divide these to beta plus and beta minus type of decays, the pattern looks like this, like shooting with a shotgun you see on your barn wall or something. So I mean, it is not giving anything, but anyway, I did this plot. So I mean, actually my student did it, not me. So again, I mean, what can we learn about this? So we can learn, this is the quenching now, or this K factor here, quenching factor, and these are the earlier studies of first forbidden unique and Gamow-Teller. And what one can see from here is that roughly this quenching is uniform for all masses roughly, and for all forbiddenness degrees. So it means that, I mean, you can maybe do some speculations. I was doing here some speculations, namely quenching factors for this interesting quantity here based on the analysis which was done by the RPA calculations in Gamow-Teller case and this first forbidden case. I have to assume that also the forbidden non-unique, which are very complex transitions, obey the same pattern. This is a very bold assumption which should be proven. I cannot prove it here, but I mean this is just the first step. I mean to excite you, unless you are sleeping. But I mean maybe this excites some people here. So one can go further to forbidden non-unique decays, which are also very interesting to study, actually a bit harder because you have scarce experimental information about these. So I of course urge every time when I give a speech somewhere I urge the experimentalists measure these transitions, and some of them are quite, I mean, somehow delighted about this and maybe think about measurements of these things here. So here I have given here a very compact expression of these decay rates here. In fact, I mean this if you expand all this, it fills several pages, several A4 pages, the expressions. But here they look rather decent. what is the key issue here? That the electron shape factor, which is here under the integral sign here, you have the shape factor. You can divide it to 3 parts. Actually, the one which is governed by vector coupling constant, and this is the one which is CVC protected one. And then you have GA here part, and then you have a mixed part, this kind of interference part, which you can use for studying the effect of GA, because there might be interference of this term with these 2 terms here, to see if you can affect these electron spectra by changing values of GA. So this is one example of a successful trial. I mean, most of these are unsuccessful. I mean, you don't have this interference, I mean, appearing in that strong way, but sometimes you are lucky and you get this kind of interference pattern, which is represented here. So you have this kind of, this even nucleus, no, this is even, this is odd, and so on. I mean, these 2 different cases here, and as you can see, when you change the GA value, the spectrum shape is changing. So this opens up a possibility for experimental interference. So I mean, in principle, one can measure this electron spectra and then compare with calculations performed with different GAs. And there are further examples like this, these transitions here in odd nuclei. You can compare different nuclear models, how sensitive these results are to different nuclear models. And this is an example of 2 different calculation interacting cell model here. This is 99 technetium going to 99 ruthenium. So interacting cell model result, and then a completely different RPA-based model, which is microscopic quasi-particle phonon model. And they are almost orthogonal in a sense, but still, as you can see, you have the similar pattern emerging. So this tells you that this is not so very much depending on the nuclear theory, and this is most striking result in a sense that this is an analysis done by using 3 different models, this quasi-particle phonon model, interacting shell model, and then in, this microscopic interacting boson fermion model. These 3 models, which are a bit different, I would say, they seem to be agreeing on the value of the effective constant, because you see this is the measured data here taken from Belli and company, and then we compared with this experimental curve, which is this solid black curve here, and obtained with all these 3 models a consistent result for this GA, which is somehow striking, I would say. So I mean, 3 different, very different, basically very different models give you one unique solution of this GA. And also we were studying, I mean, effects coming from mean field, different parameterization of the Hamiltonian and so on, and all these features seem to be independent of the fine details of your Hamiltonian or your mean field, which is very, very interesting result actually. So now one can scan through all different interesting cases here, and this is a scan through these cases. Always when you have strong sensitivity is positive, but also the branching should be almost 100% to be able to measure these transitions. So there, up to now we have here 5 cases which are strong cases for measurements, and then you have kind of moderate case here also, which in principle could be maybe measured depending how accurate your measurement is, and there are also heavier nuclei here, and we are now expanding these studies also to heavy deformed nuclei by using the IBM model actually, which is the only one who can attack actually at the moment these heavy deformed nuclei. So and also we are extending our studies to other kind of phenomena which are this enhancement of the axial charge, which is also interesting case. So this is now the conclusions and outlook. So what we learned is the surprising A-dependence and kind of unified description of this GA quenching with different model analyses. And then we have actually something like these higher forbidden transitions where you can extract somehow effective value of GA for the neutrino's double beta decay. And outlook, I would say that I would urge these measurements of electron spectra in order to have this reliable prediction for the RPA-based nuclear matrix elements, for example. Okay, thanks.